This is the circuit diagram for a three-phase semi-converter. This is arranged in a bridged pattern, but the lower portion of the circuit contains only diodes. And since this is a resistive load, we don't need to use this freewheeling diode. So again, when it comes to triggering, we only need to trigger these thyristors. But to understand the operation of this circuit, we need to go through the basics. So in this case, as we have already discussed, this D2 will be triggered as the anode of this D2 is provided with the highest voltage. But in case of a common anode system, this thing will be reversed. Since the other part of the circuit is connected to the ground, the diode with the lowest voltage in cathode will turn on. So in this case, if D4 turns on, D5 and D6 will automatically get reverse biased. So in case of a common cathode, a high voltage will turn on the diode, but in case of a common anode, the lowest voltage will trigger the diode. So if we compare it with our semi-converter circuit, we will have similar situation. And again, as the load isn't directly connected to this neutral portion, we will always get a maximum voltage which is equal to the line voltage. Unlike the previous circuit where the second terminal of the load is connected to the neutral, in this circuit no neutral connection is provided to the load. So the load voltage will always be equal to the line voltage. So we have to draw the line voltage diagram as well. So in case of a ABC sequence star connected system, the VAB will start 30 degree before VAN. So after VAB, VBC will start and the gap will be 120 degree or 4 blocks. Again after 4 blocks, VCA will start. So again, in order to draw the outputs correctly, we need to first draw the inputs correctly. You can increase the accuracy of your drawing by paying attention to these intersections. These intersections will always touch the 30 degree lines. And again, I have forgotten to mention that I have changed the orders of the thyristors as it is written in the books. So in case of a semi-converter, let me zoom in a bit. This T1, T2 and T3 seems fine, but this D2, D3 and D1, it's a little bit odd. So I have changed it to D1, D2 and D3 to maintain a symmetry. So this pattern shouldn't be memorized as it is in this book, because if you draw it like this, D1, D2, D3, it will be much simpler. So D1 is connected to A, D2 is connected to B and D3 is connected to C, just like the thyristors. So the triggering will be similar to that of a half-wave converter. These will be 120 degree apart. For the sake of simplicity, consider all of these to be diodes. So T1 will be turned on when the voltage A is highest, and D1 will be turned on when the voltage of A is the lowest. The same thing will happen in the next branch. T2 will turn on when B is highest and D2 will turn on when B is lowest. Again, when C is highest, T3 will turn on and a lowest value of C will turn on D3. Since these thyristors and diodes are connected to line voltage, we need to concentrate on the line voltage diagram. So the pair T1 and D2 will turn on when voltage of A is highest and voltage of B is lowest. So a highest A and a lowest B means highest VAB, since VAB is the difference between VA and VB. So in this portion of the waveform, the value of VAB is highest. So if we go to the conduction diagram, this portion will be suitable for T1 and D2 to turn on. So again, when VBC is highest, that means VB is highest and VC is lowest. So a highest value of B will turn on T2 and a lowest value of C will turn on D3. So in this section of this waveform, both T2 and D3 will be turned on. And again, same goes for VCA, where T3 and D1 will be turned on. So again, if we concentrate on the lower portion of the waveform, this portion here VCA is positive and here VCA is negative. So a negative VCA means VAC. So if we flip that waveform, this will become VAC. So in order to make VAC highest, we need to make VA highest and VC lowest. So in this case, T1 and D3 will be turned on. So this has been illustrated in this conduction diagram. So in this portion, T1 and D3 will conduct. So same thing goes for VBA. If we flip this portion, it will become VBA. So in case of a VBA, T2 and D1 will be turned on in this section. The same thing goes for T3 and D2. So these are probable conduction zones, as the upper portion of the bridge doesn't contain any diode. These are thyristors. So apart from this conduction zone, we need to trigger this T1, T2 and T3 in order to get conduction. So if we trigger T1 at this point of the crossover point at alpha equals 0 with respect to crossover point, the T1 will turn on and the D2 will be automatically turned on due to this low voltage at, or the lowest voltage at point B. So if we get back to our phase voltage diagram, this point of VBN is indeed the lowest voltage among all other voltages. So D2 will be automatically turned on, and if T1 and D2 is on, the current will flow from A through T1 through load through D2 to B. So the positive terminal of the load will be connected to phase A and the negative terminal of the load will be connected to phase B. So we will get VAB across the load. So in this conduction period, we will get the waveform similar to VAB. So this portion of VAB will be copied directly to the output waveform. So after this period, T1 and D3 is the probable conduction zone. Here T1 is already triggered and D3 will be automatically triggered because D3 will be triggered when the value of C is the lowest, and in this section the value of Cn is indeed the lowest. So D3 will be turned on automatically, and if T1 and D3 is turned on, we will get a voltage VA and VC, so VAC. So this portion of the output wave will contain the waveform of VAC. Since VAC is nothing but the flipped version of VCA, this VAC waveform will be positive as opposed to this negative VCA. So in this portion we are triggering T2 and D3 will be turned on automatically because the value of C is still the lowest. So T2 is connected to phase B and D3 is connected to phase C. So we will get VBC. So in this portion the output voltage will be copied from this portion of VBC. And again, after this point, T1 will be automatically turned off because T1 will be only conducting during this and this region. After this region, the T2 and D3 will conduct. So if we move a bit further, this area will be occupied by T2 and D1. So if T2 and D1 is connected, we will get VBA because T2 is connected to B and D1 is connected to A. So in this portion we will have VBA. Since the value of VAB is negative here, the VBA will be the flipped version of VAB. After that we will have T3 and D1, hence VCA, and right after that T3, D2, VCB, and again VCB can be derived from VBC by flipping it here, and after that VAB will start again for the next cycle. So VAB will be repeated. Keep something in mind, you don't need to draw the waveform beyond twice pi. So you only need to draw the waveform within the grids, so 0 to twice pi. So for alpha equal 30 degree, this waveform will be shifted 30 degree further. So the gap between this triggering will remain the same, 120 degree, just the whole thing will move 30 degree forward. So here D2 is turned on, but we are not getting any voltage until we turn on T1. So when T1 is triggered at this portion, we will have the output voltage which is equal to VAB, just like the previous diagram, but it will be shifted 30 degree. But at this point D2 will be turned off because of the fact that the cathode of the D2 is not the lowest voltage. So at this point the cathode of D3 will be lowest, which is VCN. So from that point on, T1 and D3 is turned on. So we will get VAC. So in this section, both T1 and D3 is turned on because T1 will be turned off only when T2 is turned on. So T2 is turned on at this section. So until T2 is turned on, both T1 and D3 will continue to conduct. So after that, we will have T2D3, which is VBC, and the cycle will continue. So if we increase the angle by another 30 degree with respect to this crossover point, we will have something like this, which is 60 degree with respect to this crossover point, and the relative gaps will remain the same. So in this case, we are not utilizing T1 and D2 because we are triggering T1 at this point. So from that moment on, T1 and D3 is on, and T1 will be turned on until T2 is triggered. So we will have VAC because of T1 and D3 from this portion to this zero crossing portion. After that, T2 is triggered and D1 is automatically on. So we will have VBA, and after that, due to T3 and D2, we will have VCB. If we continue to increase the angle by another 30 degree, which is alpha equal 90 degree with respect to this crossover point, here is a quick reminder. Each block is of 30 degree, so 3 blocks means 90 degree with respect to this crossover point. So T1 is turned on at this moment, so we will have our output from that moment on, and we will have VAC due to T1 and D3. But after this point, the value of VAC or VCA will go to 0. So the current will also go to 0. Since it is a resistive load, the voltage and current waveform is in phase. So as the voltage reaches 0, so does the current. So if you can remember, a thyristor turns off when the current goes below holding current. So here the current becomes 0. So it will turn off the thyristor T1. So in this portion, nothing is turned on. D1 is turned on, but D1 alone cannot complete the circuit. So in this portion, there will be a discontinuity. After that, T2 and D1 is on, and for that we will have VBA. And after another discontinuity, we will have T3 and D2, hence VCB. So this portion of VCB will continue to the next cycle. So if we analyze the VDC and VRMS equation, the span or the time period of the output voltage waveform will be same. This is 120 degree apart or 4 blocks apart. The pattern is repeating after 4 blocks. So T is twice pi over 3. I mean 120 degree. So 1 by 120 degree, and the limits are pi by 6 plus alpha. So in this case, alpha equal 90 and pi by 6 means 30. So the overall angle is 120 degree. So you can tell it by looking at the graph. The waveform is starting after 4 blocks. So 4 blocks means 120 degree, and it is stopping at pi plus 30 degree, which means 210 degrees. So in order to find the VDC, we need to find the area under this curve. So the limit will be 120 to 210 for this example. So same thing will happen for VRMS, and these formulas are elaborated in this book, page 99, 4-54 and 4-56. So these are the same equations. So this discontinuity will happen after alpha equal or greater than 60 degree. So if we get back to our continuous conduction mode, this will be restricted from alpha equal 0 to 60. So in this case, the waveform will be divided by two parts. First part is VAB and the second part is VAC. And as the pattern is repeating, we only need to consider this section, this 4 block sections, means 120 degree period. So the period will remain the same, 120 degree, and the limit will change. So the first limit will be 30 degree plus alpha. In this case, alpha equal 30, so 30 plus 30 means 60. So the starting point will be 60 degree, and the ending point of VAB is 90 degree. So in this case, 60 degree to 90 degree for VAB plus the area of this waveform. This waveform of VAC is starting from pi by 2 or 90 degree, and it ends at 180 degree. So in this example, it has started at 90 degree and it ends at pi by 6 means 150 degree plus 30 degree, in this case as alpha equal 30, so 180 degree. So if we put these values in these equations, we will get the area under these curves combined. So we will get VDC, and same thing is applicable for VRMS. And in case of alpha equals 60, both continuous and discontinuous equation will apply, because this is the verge of discontinuity. It is neither continuous nor discontinuous. So both equations will be applicable here.